Hello everybody. Well, we need to now discuss the CBSE pattern question exercises for inverse trigonometric functions. Let's begin with the first question carrying 1 mark. If sine of sine inverse of 1 by 5 plus cos inverse x is 1, then find the value of x. Let's write down the expression. The expression is sine of sine inverse of 1 by 5 plus cos inverse x is given to be equal to 1. Clear? Now obviously if sine of something is 1, that means this something, that is sine inverse 1 by 5 plus cos inverse x, will be equal to sine inverse 1. But I know that 1 is nothing but sine pi by 2. So I can write this equal to sine inverse of sine pi by 2. And I also know that sine inverse of sine x equals x if and only if x belongs to the principal domain of sine, basically that is minus pi by 2 comma pi by 2. Principal value branch, which we say minus pi by 2 to pi by 2. So over here, because the angle is equal to pi by 2 lying in this interval, therefore sine inverse of sine of pi by 2 is pi by 2. Another thing that we are aware about is that sine inverse x plus cos inverse x is pi by 2, right? And therefore pi by 2 minus cos inverse x is sine inverse x. So I can say this to be equal to sine inverse of 1 by 5 equals pi by 2 minus cos inverse x, but pi by 2 minus cos inverse x is sine inverse x. Now you all know sine inverse is a 1-1 function. Sine inverse of an angle is equal to sine inverse of the other angle. That can only be possible if both these angles are same, which implies x is equal to 1 by 5. Since sine inverse is an injective or a 1-1 function. You have got the value of x, and that completes our discussion over the first question. Second says if tan inverse x plus tan inverse y is pi by 4 and xy is given to you as less than 1, write the value of x plus y plus xy. Okay. So you are given that tan inverse x plus tan inverse y is pi by 4. Now obvious step next is to apply the formula of tan inverse x plus tan inverse y, but for that we need the condition of x into y. It is given to me that x into y is less than 1, so clearly I will be applying what? Tan inverse x plus tan inverse y is tan inverse x plus y upon 1 minus xy. This is equal to pi by 4. How can I write pi by 4? Pi by 4 can be written as tan inverse 1, isn't it? Tan inverse 1 is pi by 4 because tan pi by 4 is 1. So tan inverse of an angle is equal to tan inverse of the other angle. When we know tan inverse is an injective function, means that x plus y upon 1 minus xy is 1, which implies x plus y equals 1 minus xy, which implies x plus y plus xy is 1, and hence the value of x plus y plus xy is coming out to be equal to 1. Next question we have, write down the value of cos inverse of minus half plus 2 times sine inverse of half. Now if you remember, there was a property which we did, which inverse trigonometric functions pull out the minus sign and which inverse trigonometric functions do not. So over here we know that cos inverse of minus x is pi minus cos inverse x. It does not gulp in the minus sign, it does not take out the minus sign, it actually brings a pi in picture, and that's what it turns out to be. So in here, if I have cos inverse of minus half plus 2 times sine inverse of half, obviously cos inverse of minus half will be by the property pi minus cos inverse half plus 2 times sine inverse half. Clearly I know that cos 60 is half, so cos of, this can be written as cos of pi by 3 plus 2 times sine inverse of Sine 30 is half. So I can write over here sine of pi by 6. This is cos inverse. Now you should know that cos inverse of cos x is x if and only if x belongs to 0 comma pi, and as I just told you, sine inverse of sine x is equal to x if and only if x belongs to minus pi by 2, the restricted domain for sine inverse. Using this, you can clearly see pi by 3 belongs in 0 to pi and pi by 6 belongs in minus pi by 2, pi by 2. So eventually what you are getting is pi minus cos inverse of cos x, this will be x plus twice of pi by 6. Right? This gives you 3 pi minus pi, 2 pi by 3 plus pi by 3. So it is 3 pi by 3, which is pi. And so the answer to your very query is pi. The value of this expression is pi. Next we have if tan inverse root 3 plus cot inverse x is pi by 2, find the value of x. Okay. Again, one property which is clearly evident to be used over here is something related to pi by 2 and something related to cot inverse x. We know that tan inverse x plus cot inverse x is pi by 2, and so obviously if I am given pi by 2 and cot inverse x, I would always be wanting to club them together to bring tan inverse x in picture. So obviously in here I would be writing tan inverse root 3 equals pi by 2 minus cot inverse x. Now obviously pi by 2 minus cot inverse x is tan inverse x. Tan inverse is a 1-1 function. Tan inverse of this is equal to tan inverse of this, which implies root 3 is equal to x, and thus the value of x is clearly root 3 because tan inverse is a 1-1 function. Moving on to the next question, we have write down the value of sine of this particular expression. Okay. I have sine of pi by 3 minus sine inverse of minus 1 by 2. Now as we just discussed, which inverse trigonometric functions gulp in the minus sign, which pull out the minus sign, or which bring pi in picture and come out as a resulting value. If I talk about sine inverse, you should be aware that sine inverse actually pulls out the minus sign. Sine inverse of minus x is minus of sine inverse x. Okay? If it does that, then this expression turns out to be what? Sine of pi by 3. Now it is sine inverse of minus half is minus of sine inverse half. Minus minus will be plus, and this is sine of half. Then it is sine of pi by 3 plus sine, this is inverse. Sine inverse of half can be written as what? Sine 30 or sine pi by 6. Sine inverse of sine theta is theta if theta belongs in minus pi by 2 to pi by 2 closed interval I just had written, and pi by 6 is very much inside the interval, closed interval minus pi by 2, pi by 2. And so I am going to have the next step as sine of pi by 3 plus pi by 6, which is what? Sine of, this is 2 pi plus pi, 3 pi by 6, which is sine pi by 2, which is 1, and therefore the value of this expression is nothing but 1. Moving on to the next question, for 4 marks we have this particular expression we have to prove to be equal to 2b by a. Let's begin the computation. Over here you can see one thing, cos inverse a by b, cos inverse a by b. I am going to take cos inverse a by b to be equal to theta, which obviously implies a by b equals cos theta. If I take this as my very first step, my LHS, my complete LHS, which has to be proven to be equal to 2b by a, comes out to be what? LHS is tan of pi by 4 plus half of theta, because cos inverse of a by b is theta. So this is plus theta by 2. Then you have plus tan of pi by, this is pi by 4 itself, that's not pi by 2, it's pi by 4. Here it will be pi by 4 minus, now again this particular expression is equal to theta, so it will be theta by 2. Fine. This is what you have as your left hand side. You can see it's pretty simplified. Tan of A plus B is tan A plus tan B upon 1 minus tan A tan B plus tan of A minus B, tan A minus tan B upon 1 plus tan A tan B. Tan pi by 4 is 1, all of us know. So, simplify this, you get 1 plus tan theta by 2 whole upon 1 minus tan theta by 2 plus 1 minus tan theta by 2 whole upon 1 plus tan, and this is theta by 2. Clearly, you can take out the LCM as 1 minus tan theta by 2 into 1 plus tan theta by 2. A minus b into a plus b is a square minus b square. So, LCM is 1 minus tan square theta by 2, that's the LCM. And here you have 1 plus tan theta by 2 whole square plus 1 minus tan theta by 2 whole square. So, 1 plus tan theta by 2 whole square plus 1 minus tan theta by 2 whole square. This comes out to be what? A square plus b square plus 2 tan theta by 2 plus again a square plus b square minus 2 tan theta by 2 whole upon 1 minus tan square theta by 2. Clearly this gets cancelled out. Now that we have this long expression, in here you can see 1 plus 1 is 2, tan square theta by 2 plus tan square theta by 2 is twice of tan square theta by 2. So, 2 comes out common, 1 plus tan square theta by 2 whole upon 1 minus tan square theta by 2. You know that 1 minus tan square theta upon 1 plus tan square theta is cos 2 theta. Do we know that? Yes. Cos 2 theta is 1 minus tan square theta upon 1 plus tan square theta. Basically, the thing to be noticed is that if here it is 2 theta, here it is half of 2 theta, which is theta. So, if here it will be theta, here it will be theta by 2. I am now right now having 1 plus tan square theta by 2 upon 1 minus tan square theta by 2. Here if it was 1 minus tan square theta by 2 upon 1 plus tan square theta by 2, I would have got cos of twice of theta by 2, which is cos theta. And therefore, this turns out to be twice of, this is actually reciprocal of 1 minus tan square theta by 2 upon 1 plus tan square theta by 2. So, my answer will be 1 upon cos theta. So, 2 is already there, 2 into 1 upon cos theta, which is 2 upon cos theta, using this particular formula. 2 upon cos theta, but cos theta is what? Let's see, cos theta was given as a by b. So, this is a by b, which is 2b by a. We began with the left hand side by bringing in this manipulation in picture, and we proved it to be equal to the right hand side. Let's move on to the next question. We have with us this particular expression is to be proved to be equal to pi by 4. Now, these type of questions are pretty famous. You can see in the past year papers as well. What we do in here is we club any two. Let's club these two and then club these two, apply the same formula twice. Tan inverse A plus tan inverse B. I am talking about the computation of the LHS. My target would be to bring it to be equal to the right hand side. Tan inverse A plus tan inverse B is tan inverse A plus B 1 by 5 plus 1 by 7 upon 1 minus AB. Next you have tan inverse 1 by 3 plus tan inverse 1 by 8. So, it is tan inverse, again plus is only there, 1 by 3 plus 1 by 8 whole upon 1 minus 1 by 3 into 1 by 8. Let's begin the computation. This is equal to tan inverse LCM is 35. You have 7 plus 5, that is 12 upon 35 whole upon 35 minus 1 is 34 upon 35 plus tan inverse. Here you have what? 24 is the LCM. This is 11 upon 24 whole upon 23 upon 24. Clearly this gets cancelled out. Now you have tan inverse of 12 by 34 plus tan inverse of 11 by 23. Again tan inverse A plus tan inverse B is tan inverse A plus B upon 1 minus A into B. Tan inverse of A plus B upon 1 minus AB is tan inverse A plus tan inverse B. This actually comes out to be tan inverse of 325 upon 325, which eventually gives you tan inverse 1, and you know tan inverse 1 is pi by 4, which is your right hand side. Easy enough. Moving on to the next question we have. Prove that sine inverse of 8 by 17 plus sine inverse of 3 by 5 is tan inverse of 77 by 36. In here what are we going to do is somehow sine inverse needs to be connected to tan or converted to tan. Both expressions are involving sine inverse expression, and therefore here we need to change it to tan inverse. Let's see. I am saying let sine inverse of 8 by 17 be equal to x, which implies 8 by 17 is sine x, and sine inverse 3 by 5, let it be equal to y, which implies 3 by 5 is sine y. Fine. If sine x is 8 by 17, all of us know that sine square x plus cos square x is 1. So cos square x is 1 minus sine square x. One more thing. Sine x is 8 by 17. Fine. And x is allowed to be in the very principal domain, or what we call as the principal value branch. So x is supposed to be in minus pi by 2, pi by 2. You know that from minus pi by 2 to 0, sine is negative, and from 0 to pi by 2 it is positive. So if sine x is coming out to be a positive value, that means x belongs in 0 comma pi by 2 interval. Similarly, if sine of y is coming out to be a positive value, this implies that this y also belongs to 0 comma pi by 2. Fine. Now as I was saying, sine square x plus cos square x is 1, so 1 minus sine square x is cos square x. 1 minus sine square x. This is 1 minus 64 upon 289. 8 square is 64, 17 square is 289. This you have 289 minus 64 is 225 upon 289. So cos x is square root of 225 upon 289, which is what? 15 by 17 with a plus and minus sign. But I am not interested in the minus sign, because I know cos x will be 15 by 17 with a positive sign, because x is coming from here, and I know that cos x, if x is coming from 0 to pi by 2, it is positive, pi by 2 to pi it is negative. If x is coming from 0 to pi by 2, cos x is positive, and therefore it will be a plus sign over here prevailing. Next, in here I apply the same thing, that cos square y is 1 minus sine square y. So this is 1 minus 9 by 25, because I am squaring sine y. 25 minus 9 is 16, and so cos y is equals to positive square root of 16 by 25, which is 4 by 5. Again, I am not attaching a negative sign, because as I told you, angle is coming from 0 to pi by 2, so cosine ratio of that angle will be positive and not negative. I have cos y with me, I have cos x with me, sin x with me, cos x, sin x with me, and sin y with me. So I will be interested in computing tan x and tan y. Tan x will be sin x upon cos x. Sin x is given as 8 by 17, Cos x is coming out to be 15 by 17. 8 by 17 upon 15 by 17 is nothing but 8 by 15. And if I talk about tan y, obviously it is sin y upon cos y. Sin y is 3 by 5, cos y is 4 by 5, so 3 by 4 is tan y. This is a real number, this is a real number, so obviously why I am checking, because real numbers is the range of tan inverse, basically range of tan and domain of tan inverse. So tan x is 8 by 15, which is belonging in the range of tan. 3 by 4 is a real number belonging in the range of tan. So x will be equal to tan inverse 8 by 15 and y will be equal to tan inverse 3 by 4, because 8 by 15, 3 by 4, they are lying in the collection of all reals, which is domain of tan inverse, and x and y are actually lying in 0 comma pi by 2, which is clearly contained in minus pi by 2 open interval, which is the domain of tan inverse. And therefore from here to here, coming from here to here is a valid step. Now x is this and y is this. Now comes the main computation. You want to show sin inverse of 8 by 17 plus sin inverse 3 by 5 is tan inverse 77 by 36. Sin inverse 8 by 17 is x, sin inverse 3 by 5 is y. This expression is actually x and this expression is actually y. So you need to show x plus y is coming out to be this. Consider the left hand side, that is x plus y. X we have proved to be equal to this, y is equal to this. So this is tan inverse 8 by 15 plus tan inverse 3 by 4. Fine. Tan inverse x plus tan inverse y is tan inverse x plus y upon 1 minus x into y, which eventually turns out to be tan inverse 77 by 36, which is the right hand side. And your x plus y is nothing but the left hand side, because I have assumed sin inverse of 8 by 17 as x and sin inverse of 3 by 5 as y. That's how we have first brought cos inverse in picture from sin inverse, and then with the help of sin and cos we have brought tan in picture and hence proved the right hand side. Clear? Moving on to the next question. Solve for x. Cos of 2 sin inverse x equals 1 by 9 and x is given specifically to be positive. Okay. So here what I am going to do is I am going to let sin inverse x to be equal to y, which implies x is sin y. Clear? Let's just assume this. Therefore cos of 2 sin inverse x is equal to cos of 2y. Now if you can recall, there is this identity which says 1 minus cos 2 theta is 2 sin square theta, and therefore cos 2 theta is 1 minus 2 sin square theta. So cos 2 theta is 1 minus 2 sin square theta, 1 minus 2 sin square y. This is already given to be equal to 1 by 9. This was equal to 1 by 9, but this I have manipulated as this, so this is equal to 1 by 9, which implies 2 sin square y is equal to 1 minus 1 by 9, that is 8 by 9, which implies sin square y is equal to 2 over here in the denominator, you get 4 by 9, which implies sin y is equal to plus minus 2 by 3, or actually plus minus square root of 4 by 9, which is plus minus 2 by 3, but I am avoiding the minus sign. Why? Why am I avoiding the minus sign? Because sin y is nothing but x and x is given to be positive. That means sin y is given to be positive, so minus sign cannot come over here. Since sin y is x and x is positive. So this implies you have got x is equal to 2 by 3, not plus minus 2 by 3, minus 2 by 3 has been eradicated and therefore just plus 2 by 3 is the solution of this particular equation. And next we have proved that tan inverse of root x is half of cos inverse of 1 minus x upon 1 plus x, and x is again given to be belonging in the open interval 0, 1. This is my left hand side, and I have to prove it to be equal to the right hand side. Okay? Cos inverse expression is here, x is sitting in the argument of tan inverse. Somehow cos inverse and tan inverse need to be connected. I am going to assume let root x be equal to tan theta. Fine, which implies tan inverse of root x is equal to theta. So basically I am trying to take tan inverse root x to be equal to theta. If you consider the right hand side, you have 1 by 2 cos inverse of 1 minus x upon 1 plus x. Clear? I can write this to be equal to 1 by 2 cos inverse of 1 minus root x whole square upon 1 plus root x whole square. Obviously, because I need to bring root x in picture, that is what is sitting in the argument of tan inverse on the left hand side. Now you have 1 by 2 cos of root x we have taken as tan theta. So this is tan square theta, and this is 1 plus tan square theta. I just told you that 1 minus tan square theta upon 1 plus tan square theta is cos 2 theta. So this is half of cos 2 theta, which is equal to, this is cos inverse, half of cos inverse of cos 2 theta, which is 2 theta, and this is equal to theta. Theta is what? Tan inverse root x. Tan inverse root x. And this is your left hand side. So over here we just began in an opposite fashion. We began with the right hand side, proved it to be equal to left hand side by first simplifying the left hand side from tan inverse root x to just a small theta, which eventually gave us an expression for root x as tan theta, which helped us apply a formula of 1 minus tan square theta upon 1 plus tan square theta to be equal to cos 2 theta, and that made cos inverse and cos basically come together in picture to just deliver me my left hand side. Is it clear? That completes our discussion over the questions. That's it from my side. Thank you.